All right, greetings, greetings. Hello, everybody. Welcome back. Today we're going to be doing section 3.7, all about factoring polynomials, and finally the fundamental theorem of algebra. This is going to finally round out our study of polynomials, and we're going to see just how powerful that fundamental theorem is. Let me go ahead and pull up the slides, and let's go. All right, so we're going to start with some motivation. Oops. There you go, some motivation. Then we're going to talk about the Euclidean division algorithm, like we talked about back in chapter 1. Then we're going to generalize it to the polynomial division algorithm. Then we're going to state and prove this theorem, the remainder theorem. And from that theorem, we get the factor theorem, which we talked about back in section 3.5. Then we're going to get what's called the rational zeros theorem. This is a really helpful theorem that lets you determine if there are any rational zeros of a polynomial. Then, to kind of complete things, now that we've talked about complex numbers, we're going to need to talk about complex variables and complex polynomials. Then we can finally state the fundamental theorem of algebra, all right? Following that, we're going to see some important corollaries, and those are really going to be the main tools that we use, those important corollaries. Then we're going to finish up with some helpful technology. Mathematica can help with our analysis of polynomials in some incredible ways, so I'm excited to show you some examples of that. All right. So start with the motivation. We learned how to factor quadratics earlier on in the section, and we mentioned and kind of talked about that the process extends to polynomials as well. But the question is, how do we actually factor a polynomial? If the degree is high, like if it's degree, 7, 8, 9, how do we factor that? It's not like a quadratic function where we have these tools to do it, right? Where we just have like the quadratic formula, for example. So if you remember from chapter 1, when we factored integers, we used the Euclidean division algorithm to test divisibility of one number by another number. Basically, we were like, okay, if we can divide this number by this number and we don't get a remainder, then we know that that result, that divisor is a factor of the number, right? So, sorry, if there was no remainder. So if the remainder is 0, then that means we have a factor. If the remainder is not 0, then we did not have a factor, right? So for polynomials of low degree, that may not be too difficult to just try to factor by hand, right? If the degree is 3 or 2. But when the degree gets even a little bit high, it really becomes inefficient for a human to take on the task by hand. And so that's why we use computers, okay? That's the kind of the basic idea. So just a little refresher, if you remember, this is Euclid's division lemma. This is actually a consequence of Euclid's division algorithm. So just to kind of refresh our memories of it, if we had integers a and b with b not equal to 0, then there exist unique integers q and r such that you could write a over b as q plus r over b. Just like that, where this r is less than the size of b, and r is greater than or equal to 0, right? And then we had these vocabulary terms, right? A over b is the ratio. This number on the top, that's called the dividend. This number on the bottom, that's the divisor. Q is what we call the quotient. R is the remainder. And then this whole piece, r over b, that's the fractional part of the ratio, the fractional part of a over b, right? That's what it is. So just a quick reminder, these are some examples. I'm not going to walk through them in detail, but it's basically just doing division like you remember from back in grade school. You do the division algorithm here. And in this case, 79 divided by 7 leaves you with a remainder. You've got a remainder of 2. So what that tells us is that 7 is not a factor of 79 because we're getting a remainder. And what we can do is we can actually write 79 as this quotient times 7 plus this remainder. That's the basic idea, right? Okay, now compare that to this process. Let's look at, 91 divided by 7. And you'll remember that if a number divides another number, quote, evenly, then that means there's no remainder term. That's what we're getting in this case. So 91 divided by 7 leaves us with 13 and a remainder of 0. So we can fit 7 into 91 13 times. And we'll have nothing left over when we do that. Oh, wait, I have a little typo right here. Let me fix this. This should say 13. That should say 13, and that should say 13. And that should say 13. There we go. There you go. I'll just write them all as 13s. There you go. So in other words, 7 is a factor of 91 because when we divide 91 by 7, we don't get a remainder. We just get the quotient, which is 13, and then we get nothing else, right? Okay. Now, we're going to see how that extends to polynomials now. So the polynomial division algorithm is basically the same process as the standard Euclidean division algorithm for integers, but it's applied to polynomials. It's a result of the Euclidean division lemma for polynomials, which is very, very similar to the division lemma for integers. So we're going to take a look at that right now. And I want you to just maybe just relish how funny the equivalence is. They are almost the same statement, just in the realm of polynomials instead of integers. Here we go. So this is Euclid's division lemma for polynomials. Let a of x and b of x be polynomials, and suppose that b of x is not equivalently zero, meaning it's not just equal to zero for every x. Then there exist unique polynomials q of x and r of x, such that you could write a of x over b of x as q of x plus r of x over b of x, right? Where r is either equal to zero or the degree of r is less than the degree of b. Pretty wild, huh? It's pretty much the same statement, except some little tweaks to have it apply to polynomials. Let's go over the vocabulary. The vocabulary is identical, really. A of x over b of x is what we call the rational function. A of x is the dividend still. B of x is the divisor. Q of x is the quotient. R of x is the remainder, and R of x over B of x is called the fractional part of A of x over B of x. So it really is very similar. In fact, let me let me flash back to the one for integers real quick. This is the one for integers, and this is the one for polynomials. So really, really very much the same, except in a different context, right? Okay, so now we need to talk about an important interpretation of this lemma and the result that it gives us. And we're going to use this interpretation more in section 3.9 especially, but also section 3.8. This is going to help us study rational functions, which is how we're going to close out the chapter here, chapter 3. So what I'm going to do here is this. So if you notice this form, we can rewrite this rational function as a quotient plus a fractional part, right? Well, we're going to relabel this fractional part as d of x. And we're doing that intentionally. Maybe this notation seems familiar now. D of x is actually a difference function. It is quite literally a difference function. And the reason we call it a difference function is because d of x is just equal to the original rational function minus the quotient. So basically, if you take this equation and you solve it for d of x, if you basically just subtract q of x from both sides, you will get this result. So in a very real sense, you can think of d of x as a difference function. It's telling you the difference between the rational function a of x over b of x and what's called the polynomial asymptote, the polynomial q of x. All right. I will also call it a non-vertical asymptote. The technical term for it is curvilinear asymptote, and we're going to spend section 3.9 studying those things in great detail. So this is kind of a setup for that, right? But I want you to think of this remainder here, or this fractional part, as a difference function, the difference between the quotient and the original rational function, right? Okay, now let's do the process, okay? If you remember how to do this, great. If you don't, that's totally fine. We're going to get lots of practice doing it. We also have mathematical technology to help us, but we're going to try to do this division problem here. We're going to compute this polynomial divided by this polynomial, which I've equivalently written here as this ratio, okay? This is one where, you know what, I'll show you how to do this one, and then you can try the next one on your own, okay? So here's how the process goes. Uh, Again, if you know how to do this, or if you know a different way to do it, totally fine. Use the way you know how. I'm just going to explain how I like to think of it, okay? Hopefully I don't mess it up too bad. All right, so what I'm trying to do is I'm trying to divide this number here by this number here. And so we like to set it up with this kind of bar symbol. Frankly, different schools and just different countries do this process very differently. So again, you can do it your own way if you have your own way to do it. But what we do is kind of the same thing we did with the regular division algorithm. We're going to start here and we're going to ask ourselves, what do we multiply this by to get 3x cubed? So what do I multiply x squared by to get 3x cubed? The answer is 3x. X squared times 3x equals 3x cubed. And so I'm going to write 3x right here above the linear term x. Okay, so x squared times 3x equals 3x cubed. Then I'm going to multiply 3x by 1, and 3x times 1 is 3x. So then I'm going to do this. I'm going to write 3x cubed below, and I'm going to write 3x here below the linear term, and then I'm going to subtract those. Remember with the regular division algorithm for integers, right? You would subtract that value from the expression above. We're doing the same thing. So we're going to subtract these things from the polynomial above. And as we do this, we should end up eliminating a term at each step. So 3x cubed minus 3x, that's 0. That's why there's nothing there. 4x squared minus 0 is just 4x squared. X minus 3x is negative 2x. And then we bring down the 7, just like that. Very similar to what we did with integers. Then we repeat the process. That's why this is an algorithm. This is a loop. You could program this. CS majors, that's actually a very typical undergraduate project for you to do, is to code the division algorithm by hand using loops. It's a classic exercise for CS majors. All right, so let's repeat the process. What do I multiply x squared by to get 4x squared? 4. So I write 4 right there above the constant term. So 4 times x squared is 4x squared. I'm sorry, 4x squared. And then 4 times 1 is 4. Then I subtract those two results, right? So I'm going to subtract this and subtract this, and then I just keep going. All right, so 4x squared minus 4x squared is 0. That term disappears. Negative 2x minus 0 is negative 2x. 7 minus 4 is 3. And now we are done, okay? We're done because the degree of this resulting polynomial is less than the degree of the divisor here. So at this point, we can stop. Yeah, it's basically like getting a remainder. And in fact, this is the remainder term for this particular division problem. So what we've done is this. We have rewritten this rational function in the form that's given by Euclid's division lemma. We wrote it as a quotient plus a fractional part. And notice again that the degree here on the top is less than the degree of the denominator, strictly less than. Another way we could write it is we basically showed that this polynomial in the numerator is equal to the quotient 3x plus 4 times the divisor x squared plus 1, but then you have that remainder, right? You have that remainder there. So we could say that this expression, this polynomial, didn't divide this polynomial evenly, right? You end up with a remainder term. Okay, now I want you to try this one, okay? So I want you to try this one on your own. You're going to do this polynomial divided by this polynomial, and try to follow the method I just did there, or if you have your own method, do it yourself. So as usual, just kind of think about it for a minute. All right, now you know what you got to do next. Say something out loud. Better yet, if you're watching this with your peer, talk to them, talk to your friends, talk to your dog. Say something out loud, maybe what you're going to do first, or maybe how you will write it. Okay, and now try to work it out on your own, and we'll do it together. Okay, all right. So for those of you that did try this at home, let's see how you did. You might have noticed there was some kind of funniness going on here. We're going to explain that in just a minute. So here's the setup for it. Same kind of deal. We're writing this polynomial, the dividend right here, and the divisor goes right here. But here's the thing. Algorithms are algorithms. They're not intelligent. They're just processes, right? And if you don't set things up for the algorithm to work exactly right, the way that it needs, sometimes it'll fail, right? This is one of those situations where we need to do something very specific to get the algorithm to work the way it's supposed to. And in this case, what we need to do is we need to include a 0 term. So you'll notice that the polynomial that we're dividing, it was x to the fourth minus 3x cubed plus 2x minus 5. It's missing a squared term, or maybe more precisely, what I can say is the coefficient of the squared term is 0. 0x squared. Now, because this algorithm is very much just an algorithm, you have to include that gap. You need to include that zero term so that way the powers of the terms decrease consecutively. 4, 3, 2, 1, 0. That's how you keep everything lined up. You got to leave some space. You don't always have to leave some space, but if you're just kind of following your nose through this process, you're going to need to leave that space. Now let's walk through the steps again, and I know this is going to get tedious because I know I'm going to sound like a broken record a bunch of times now. All right, here we go. What do we multiply x squared by to get x to the fourth? X squared. So we're going to write x squared above that squared term. All right, x squared times x squared is x to the fourth. X squared times negative x is negative x cubed. X squared times 1 is x squared. Then we're going to change all the signs because we're going to subtract. Usually when I do this by hand, I really just follow my nose. I just write the resulting terms and then change all the signs at the end, okay? But this is calculated automatically, so it's changing the signs for us. All right, now we subtract or we add those results, right? X to the fourth minus x to the fourth is 0. Negative 3x cubed plus x cubed is negative 2x cubed. 0x squared minus x squared is negative x squared. And then we bring down this term, working our way through just like with integers, right? Bring down this term, repeat the process again. So here we go. What do I multiply x squared by to get negative 2x cubed? What do I multiply this by to get that? Negative 2x. So I'm going to write negative 2x up here. Now I just follow my nose. Negative 2x times x squared is going to be negative 2x cubed. The sign changes. Negative 2x times negative x is positive 2x squared, but then the sign changes. Negative 2x times 1 is negative 2x, but then the sign changes. And now I add. Here we go. That gives me 0. This gives me negative 3x squared, and this gives me 4x. Then I bring down the negative 5. Then I keep going, right? We keep going until the degree of the result, the degree of the result here is less than the degree of the divisor. So we got to keep going, right? There's a stopping or a halting condition, and that halting condition is when the degree of this result is strictly less than the degree of the divisor. So we got to do it one more time. Here we go. All right, what do I multiply x squared by to get negative 3x squared? Negative 3. So I write negative 3. All right, negative 3 times x squared is, negative 3x squared, sign change. Negative 3 times negative x would be 3x, sign change. Negative 3 times 1 is negative 3, sign change. And then now I add the results. There we go. Or subtract, however you want to think about it. Yeah, subtract the whole line or add the line after you've applied the negative change. All right, we get 0, we get x, and we get negative 2, and we're done. The degree of this is 1, the degree of this is 2. So the process terminates, and now we can write our rational function in the form given by Euclid's division lemma. Here it is. So this can be written as this polynomial plus this remainder over the divisor, just like so. In other words, we rewrote that polynomial in the numerator as this quotient times the divisor, and then there's a remainder. There's a little bit left over. So again, this is a situation where x squared minus x plus 1 does not divide this polynomial evenly. Or in other words, x squared minus x plus 1 is not a factor of the numerator, right? Always go back to your intuition and remember what we were talking about with the standard division algorithm for integers, right? If you end up with a remainder, that means the divisor is not a factor of the dividend, not a factor of the thing that you're dividing, right? Okay, here is another one. Let's try this one, okay? Actually, I want you to try this one on your own to just give you a little more practice. So think about how you're going to do it. Give your brain some verbal feedback. Say out loud what you're going to do, maybe how you're going to do it. And then work it out on your own, and we'll do it again or do it together in a moment. Okay, here we go. Same process. We don't need to include any zero terms here. The powers are decreasing consecutively, 2, 1, 0, so we're all good. When we do the division, we get this. And check this out, 0. 0. That means we have no remainder in this case. So that means that this original rational function here is just equal to x plus 4. Or in other words, when we divide the numerator by x minus 7, we get x plus 4. This is helpful because what this tells us is that x minus 7 is actually a factor of x squared minus 3x minus 28. So that means we could write x squared minus 3x minus 28 as x plus 4 times x minus 7, just like that. And maybe now let's pause for a second. Look at this expression here, this quadratic, and factor it. Try factoring it. Two numbers that multiply to negative 28 and add to give you negative 3. Let's see, 7 and 4, negative 7 plus 4. Okay, so x minus 7, x plus 4. There it is. Cool, huh? So the division algorithm is basically generalizing the process of factoring. And what we're really looking for is we're looking for stuff that has no remainder, okay? All right, next, which one? Yeah, okay, let's try this. Look at the similarity here between these two problems. What do you think is going to happen if this 28 changes to a 30? What do you think is going to happen? Just let me throw the thinker up for a second. Okay, now say it. Say it out loud. What do you think is going to happen? All right, let's take a look. When we do the division, we're going to end up with a remainder. In fact, we're going to end up with a remainder of negative 2. So here, I mean, x minus 7 is not a factor of x squared minus 3x minus 30. There's a little bit left over when we do that. We're going to be left with a remainder of negative 2. So we could write this as x plus 4 plus negative 2 over x minus 7. But one thing I want to point out, well, maybe I'm not going to jump in the gun a little bit too much here. Look at the difference in these results in the remainder. This one was a 0. This one was negative 2. Think about that for a second. Okay. All right. So there's something special going on here and something that's really going to help us with our analysis of these types of functions and just dividing polynomials. If the divisor b of x is a linear function of the form x minus c, like we just saw a second ago, then the division lemma is asserting that the degree of r of x has to be 0. All right, the degree of this resulting function has to be 0. And that's because the division lemma says whatever this remainder is, the degree has to be strictly less than the divisor, right? Even what we were seeing when we did the division process. So if you remember, a polynomial that's degree 0 is a constant function, right? Degree 0 functions are constant. So what that means is we could write that remainder function, r of x, as just r for some number r. It's going to be some number. Doesn't really depend on x even. It's just going to be a constant, right? No matter what x is, it's going to be r. There we go. So looking at this a little more technically, we could write our function. Oops, sorry, maybe this should say a, just for clarity here. Let me see. Yeah, make this a. There we go. There we go. Okay, that means we can write a of x as q of x times x minus c plus some r, some number r, right? But consequently, look what happens when we actually plug in the number c here. So we're going to plug in c for our input, and we're going to get, oops, this should also say c. Oy, too many typos. Hang on a second. There we go. Okay, sorry about that. So let me just fix those typos. So what we just found out is we can write a of x as q of x times x minus c plus r, right? Now, when we plug in the number c to our function there, that numerator, we get q of c times c minus c plus r. But c minus c, that's equal to 0. So this whole term is going to disappear, and what you're left with is r. In particular, a of c equals r. So what that means is when we evaluate this numerator, this dividend a of x at this number c, we're getting r. We're getting r, which is the remainder that we would get when we divide by x minus c. And that proves the theorem called the remainder theorem. That's what we were looking for. So let f be a polynomial. When f of x is divided by x minus c, the remainder is f of c. This is a really, really powerful result because what it does is it lets us check to see if a number is a zero of a polynomial just by evaluating the polynomial at that number. It also tells us what the remainder is going to be if we were to divide by the linear factor associated with that zero, right? That's the big idea. So this is one that I want you to try, and these questions are pretty straightforward, but maybe I should do this first. Just ponder this for just a moment here. Think about what that says, okay? And then read it out loud to yourself. Maybe even phrase it in your own words. Okay, now let's practice it. So this is one I want you to try on your own. I want you to find the remainder of this polynomial when it's divided by x minus 3, all right? So this one, just go right to it. See if you can do it directly. Find the remainder of that function when you divide it by x minus 3. All right. Okay. Well, by the remainder theorem, all we need to do is evaluate the function at 3. And whatever that number is, that will be the remainder if we were to divide by x minus 3. So here we go. When I plug in 3 for x, I get this, which simplifies to 27 minus 45 minus 8, which is negative 26. So by the remainder theorem, the remainder would be negative 26. So if I tried to compute x cubed minus 5x squared minus 8 divided by x minus 3, what we're going to get is we're going to get some, oops, that should be a q, my bad, q of x times x minus 3 minus 26. That's what we're going to get when we do that division. Not sure what q of x is going to be yet. I've got to actually go through the division algorithm to do that, but I do know that the remainder will be negative 26. All right, now this is where we can leverage this theorem. Here's another question. I want you to do this one on your own. Is this polynomial divisible by t minus 1? Is it divisible by t plus 2? Try it. Think about it. And I'll say this, don't just do the division. Don't do the division outright. Use what we just talked about. Think about it for a sec. Right. Now verbalize something. What could you try? Right. Now try to work it out on your own. All right. Okay, so we don't need to actually do the whole division, the whole division process to see if this polynomial is divisible by those two factors. We just need to evaluate the polynomial at those potential zeros and just see what we get. If we do not get 0 as a remainder, then that means it's not divisible by that factor. If we do get 0 as a remainder, then we have found a factor of that polynomial. Wow, that's amazing. Here, let's check. Okay, if I test 1, if I plug 1 into this, I get negative 18. Negative 18 is not 0, right? So this function is not divisible by t minus 1. T minus 1 is not a factor of this polynomial. Let's check negative 2, right? Negative 2, take the opposite of that sign. Um, let's plug it in. When we plug that in, we get negative 2 cubed minus negative 2 squared minus 10 times negative 2 minus 8. And that's 0. That's actually 0. So that tells us that indeed this polynomial is divisible by t plus 2. So that means if we wanted to continue with the process of factoring this polynomial, we would know we could divide by this, and then we would get a smaller polynomial, a polynomial that's a degree less. That's a factor of this thing right here. That's the big idea, okay? Here's the actual process. I computed both of these here. If we divide this by t minus 1, we get a remainder of negative 18. There you go. But if we divide this by t plus 2, we get a remainder of 0, and we get the resulting quotient. We get the resulting quotient, t squared minus 3t minus 4. In other words, this thing here is equal to this thing times this thing. And now, this is why we learned how to factor quadratics, because now if you wanted to continue the factoring process, you then just need to factor this quadratic expression here. Um, I'll let you do that one on your own. See if you can find two numbers that multiply to give you -4 and add to give you -3. Right, maybe you can do that in your head now. All right, so from the remainder theorem, we get this corollary, and this is a helpful corollary, maybe even a little bit obvious if you just kind of think about it intuitively. A polynomial function can have no more zeros than its degree. So for example, this polynomial here, it's degree 3, and what this means is that it can't have more than 3 zeros. So that's really, really handy. The degree is basically an upper bound on the number of zeros that a polynomial can have. That's what this says, right? Now, there is still the issue of finding the zeros, because I mean, we could just guess any number, right? If we're given some polynomial like this, I mean, what could possibly be a zero? 0, 1, 2, -10, 15, like what could we could guess anything, right? There's infinitely many choices. So there is a really handy theorem that can narrow things down quite a lot. Not completely, but quite a lot. And that theorem is called the rational zeros theorem. All right. It's also called the rational roots theorem. So if you like look it up online, you could look for rational roots theorem. I'm going to read the definition and then try to give you some intuition for it, and we'll do a couple examples as well. So here we go. Let f be a polynomial function that's degree 1 or higher in standard form. So this is the standard form of a polynomial, like we saw back in 3.5, right? Here we're requiring that the leading coefficient is not 0. We're also going to require that the constant term is not 0. All right? So polynomial in standard form with leading coefficient and constant term non-zero. And we're also going to require that each one of these coefficients is an integer, all right? Integer coefficients, all right? Positive and negative whole numbers. Yeah, all right? So if the number p over q in lowest terms, that rational number, if it's a rational zero of f, then p must be a factor of the constant term, and q must be a factor of the leading coefficient. Uh, I can barely understand what that means, right? This is one of those theorems that is technical when written out, but in practice becomes uh, pretty straightforward. So let's get some intuition for it. So in practice, what this does is it gives you a systematic way of checking for rational zeros. You basically just need to check all the factors of the leading coefficient divided by all the factors of the constant term. Okay, that's really what it's saying. However, maybe if you kind of remember how it was when we were factoring things back in chapter 1, this method can be very tedious if the leading coefficient or the constant term have a lot of factors. It's really nice if those numbers are prime, but if those numbers are highly composite, then you've got to check a lot of numbers. Very tedious. There's another catch to this theorem here. It doesn't guarantee the existence of a rational zero, as we're going to see in a few minutes here. Only that if there is a rational zero, it has to have a certain structure. That's it. So the other thing is it's often the case that a polynomial has no rational roots. Um, this is why it's important to understand irrational numbers, because a lot of times these polynomials, a lot of times their roots are irrational. But hey, this helps us limit some things a little bit, right? At least in this case, what we can do is we can check to see if there are any rational roots, because if there are any rational roots, they have to have this form. Let's try one. Let's try one, okay? All right, so we're going to find all the possible rational zeros of this polynomial here. And I wanted to pick one that was a fairly large degree. It's degree 5. We don't want to have to just guess and check every number, right? I'm going to do this one. I'm going to do this one, and then you can do the next one on your own. But the rational root theorem basically says, first, find all the factors of this, then find all the factors of this. Divide those results, and whatever those rational numbers are, those are the only possible rational zeros. So here we go. The factors of -6 are these: plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Yeah, you got to include the negatives too. Positive 1 and negative 1. Positive 2 and negative 2. Positive 3, negative 3. Positive 6, negative 6. Now, all the factors of 2, whew, thankfully 2 is prime. Positive negative 1, positive negative 2. Okay, so we're looking at this divided by this now. We're going to take all the factors of this and divide them by all the factors of this, and we're going to get a lot of results. Boom, that's all of them. Oof. Oof. Now, if your head is kind of reeling or if you're starting to feel a little overwhelmed, don't worry. That's a normal response. Um, you're totally sane. Nothing, that's exactly what everyone feels. But just take a deep breath. We can walk through this, we can work through this. We've got help, we can help each other, and we have computers as well. Let's make sense of the process and see what's going on. So when I look at this list, there are some duplicates in this list too. We can also just rewrite this as 1, 2, 3. Oh, look, 2 over 2, that's 1. So the list reduces a little bit. And then when you look at all of the remaining possible zeros, you get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/2, plus or minus 3/2. And what the rational zeros theorem guarantees is that if this function has a rational zero, meaning if one of the, let's say, x-intercepts is a rational number, then it has to be one of these, has to be in that list. So we've limited the number of possible rational zeros quite a lot. So we don't just need to check any random guess. We don't need to be like, we don't even need to bother checking the number 4, for example, or the number 5, or the number 7. If there's a rational zero, it's got to be in this list. So now we've reduced our work to having to only check 1, 2, 3, 4, 5, 12 possible rational roots. All right. Now, just a reminder, these are just the possible rational roots. That doesn't mean that this thing has rational roots, just that if it does, it's in this list. This also completely disregards irrational roots or irrational zeros. Those are not in this list. So this only helps us a little bit with our analysis. But you know what? At least it takes care of all the rational numbers, which isn't bad, right? That's pretty good. Okay, now I want you to try this one, and let me see. Yeah, okay. This is a long example. It's a good one, but I want you to at least start it, okay? You don't have to do the whole thing. Start by, let's see. Okay, I want you to try to use the rational roots theorem to start, and then we'll continue from there. So start looking at this polynomial here. I want you to give the list of all the possible rational zeros that this function has, okay? Think about it for a minute. All right. Now, say one or two of them out loud. What's a possible rational zero that you can see? Okay. Now, write them down. Write down the list of all of the possible rational zeros of this polynomial. Sweet. Okay. All right, so what we're going to do is this. We're going to find all of the real zeros, not just rational, but rational and irrational, and we're going to factor it. Because remember, if we know a zero, then we know a factor, right? There's that connection between linear factors and the zeros, the factor theorem. So a really good place to start is the rational roots theorem. Unfortunately, 36 is a highly composite number. Yeah, there's a lot of rational zeros. One thing we know is the degree here is 5, so there are no more than 5 real zeros, right? There can't be any more than 5. That's it. So there's only 5 things that we're really looking for. But 36 has a lot of factors. Luckily, the leading coefficient is 1. That's always nice when the leading coefficient is 1. And now there are 18 possibilities for rational zeros. Oof. So we would have to check all 18 of those. Well, let's just start at the bottom. Let's make a guess. Let's just try 1. So if we check x equals 1 and we plug x equals 1 into our polynomial, we get 1 minus 5 plus 17 minus 49 plus 72 minus 36. which is 0. So by the remainder theorem, that means the remainder is going to be 0. And so that means that x minus 1 must be a factor of this polynomial. Bravo. Yes, we are on the way. Now that we know a factor, we can use the division algorithm to factor this by x minus 1. I won't do the whole process here. You are welcome to try it, but we've already seen it a couple of times. You would just do that. You would literally just go through the division algorithm with x minus 1. And when you get to that, when you get to the end of that, you'll find that you can rewrite this as this. There we go, just like that. So notice here, we pulled this factor out of here, and what's left is a degree 4 factor. And this thing here, it actually results in what's called the depressed equation of P. Um, I would say pun not intended, because getting the degree to be a little bit lower makes me feel kind of good. I don't know if I would say depressed, but the idea here is that you've depressed the equation that you were trying to solve by 1 degree. You've like lowered the degree by 1, and now the process repeats. So now we are stuck with a degree 4 polynomial, and we need to find all of the zeros of that degree 4 polynomial. What could we do? Well, these are all integer coefficients. Rational roots theorem is a good place to start. Unfortunately, this constant term is still 36. Fortunately, the leading term is 1, so we would still have 18 factors to check, all the ones that you previously saw again. So repeating that process, which I'm going to skip, repeating that process, checking x equals plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, reveals that 2 is actually a 0 of this polynomial here. And because 2 is a 0, that means x minus 2 is a factor. Do the division algorithm again, run through the division algorithm, and we can rewrite this degree 4 polynomial as x minus 2 times this degree 3 polynomial. And now we repeat the process. But again, there's lots of ways you can proceed. Like when the degree gets low enough, when the degree gets to be around 4, 3, especially 2, we have other methods to proceed from there. So what we could do is here we could repeat the process. We could use the rational zeros theorem, see if there are any rational zeros. We could test them all. Or since we learned this process earlier, we could actually factor this by grouping. Now we're at a stage where we could factor that by grouping. We could factor out x squared from both of those. We could factor out 9 from both of those. And when we do that, we get x minus 2 times x squared plus 9. So this thing factors as this. Sweet. See, now all those techniques are coming together. That's why we learned them earlier on. Remember, like way back in section, geez, 3.2, maybe 3.3, where I was like, what's the motivation? Why do we care about factoring quadratics? This is why, because once it gets low enough, we have easier methods to factor it. We don't have to use rational roots theorem and all that stuff, right? Okay, now we are, I'll say, nearly complete. We're complete in the sense that we did find all of the real zeros. We just factored this function. We rewrote this polynomial as x minus 1 times x minus 2 squared times x squared plus 9. We have now factored this function over the real numbers, okay? Now, this is why we talked about factorization domains earlier. X squared plus 9, you can't factor that over the real numbers, right? There's no real number x such that x squared equals -9. So what we call this is an irreducible quadratic factor, or a prime quadratic factor. Maybe the word sounds familiar. But it is only irreducible over R. We can't factor it over R, but we can factor it over C. We can factor it over the complex numbers. So if we allow ourselves to use complex numbers, we can factor even further, all right? And that's where we pivot a little bit to talk about complex variables and complex polynomials. This is why we talked about complex numbers. Without getting too crazy about it, all we're going to do now is allow ourselves to use complex numbers. So I'll read the definitions, but the big idea is let's use complex numbers so we can make this exploration more complete. So what is a complex variable? It's a variable that is complex valued. That's it. What is a complex function? A complex valued function, or just a complex function, is a function whose output is a complex number. That's it. Functions of a complex variable are complex functions. What is a complex polynomial? It's a polynomial where the input or the coefficients are complex numbers. That's it. So big idea is now we can throw complex numbers into this whole mix and we'll see how it goes. Okay. This little bit about notation, I mentioned this before. So just to kind of remind you, a lot of times when we're dealing with complex numbers, we like to use the variable z, the letter z, instead of x, because x and y already have, they already kind of have a notation, right? They already have a, oh gosh, what's the word? We've already used them when we're talking about real numbers and the xy plane, right? So we're going to let z represent a complex number, and that way we can also just write it as x plus iy, and then it really corresponds with the xy plane. Okay. All right, so what is a complex polynomial? Well, basically, it's a polynomial where you're allowed to use complex numbers. That's it. Here it is written in standard form. N is a non-negative integer, except now the coefficients are allowed to be complex numbers. For example, here is a complex polynomial, 2i times z to the fourth plus 7z squared minus 5 plus 3iz plus pi. That's a complex polynomial. Another note, very similar to polynomials of a real variable, the domain of any complex polynomial is everything. It's all of the complex plane. So there's no numbers that are going to cause problems here when we're working with complex polynomials. Everything is acceptable. All right. Okay. Now, similarly, we have something that is called a complex zero or a complex root. So if we've got a complex valued function of a complex variable z, if there is a complex number r that makes this function evaluate to zero, then we call that a complex zero of the function, or we call it a complex root of that zero equation right there. So as an example, 3i is a complex root of, or complex zero of z squared plus 9. Because if I plug in 3i to this function, then I'm going to get negative 9 plus 9 equals 0. So this is a complex root of that function. That's the basic idea. Okay. Now, one thing I'll say is remember that the set of real numbers is contained in the set of complex numbers. So every real zero of a complex function is a complex zero as well, right? Real numbers are also considered complex numbers. This also means that every real valued function could be interpreted as a complex valued function where you set the imaginary part of the input and the output to zero. Remember that quote from Jacques Hadamard, the shortest path between two truths in the real domain passes through the complex domain. This is kind of what he meant by that, right? Now, this might feel a little bit overwhelming, so I just want to assuage any worries a little bit here. Most of the time in this class, the coefficients of our functions are going to be real numbers. A lot of times they're going to be integers, okay? But it's important to always keep an eye toward generalization or abstraction with the techniques we learn, right? This is not the end. We can go much, much farther. Like I was saying on day one, there is no highest math class. It's like a rabbit hole that you can go down forever and ever. You just decide to choose when you don't want to go down the rabbit hole anymore. So always have an eye toward generalization. And I'll say appreciate when things are easy. It's always nice when things are easy, right? Okay, here we go. The buildup. We have done it. We are now ready to state the fundamental theorem of algebra. And you might be surprised that the theorem is really quite simple. The fundamental theorem of algebra says every complex polynomial of degree n greater than or equal to 1 has at least one complex zero. That's it. That's it. So every complex polynomial that's degree 1 or more must have at least one complex zero. That is the fundamental theorem of algebra. Very simple statement. We are not going to prove that theorem in this class. Sometimes the proofs that, I'm sorry, the theorems that have the simplest statement are the hardest to prove. The reason that we're not going to prove it in this class is because it actually requires complex analysis to prove it. You could also use topology, but those are more advanced in this class. You're welcome to look up the proof and try to follow it, but the one that I always fall on is the one from complex analysis. Math majors, almost certainly you will have to prove this theorem on an exam in one of your math courses, either undergraduate complex analysis or graduate complex analysis. That'll be a test question, guaranteed, guaranteed. All right. Um, Now, here's what we're going to do in this class. We're going to leverage all of these things that we have been building up for so many sections, like 7 sections more, right? We're going to leverage it to make things really easy, or maybe just, well, allow us to do a more interesting analysis. Here we go. We're going to use the fundamental theorem of algebra and the factor theorem to yield this powerful corollary, which I stated a while ago, but now we're going to prove it. Every complex polynomial function can be uniquely factored into a product of linear factors. Okay, huge result. This means that if you've got a polynomial and you're allowing yourself to work with complex numbers, you can factor it all the way until you end up with only linear factors raised to some multiplicities, right? We don't know what the multiplicities are necessarily, but anytime you see a polynomial, you can factor it. You can factor it all the way down until every factor is linear if you allow yourself to use complex numbers. If you only allow yourself to use real numbers, remember you can factor it all the way down until you have linear or quadratic factors, just like we saw in the previous example, okay? These numbers here, those are going to be all the zeros of the polynomial, and these are going to be the multiplicities of those zeros. And, and because we are factoring over the complex numbers, every complex polynomial of degree n has exactly n complex roots. So in other words, the degree is equal to the number of zeros. And how do you find them? You add up all the multiplicities. That's it. That's it. If you're only factoring over the real numbers, you have to be a little bit careful because you'll have quadratic factors, and so you'll have to take that whatever the multiplicity is and multiply it by 2. So it's a little less complete, right? It's a little less complete when you only allow yourself to work with real numbers. Complex numbers finish the job, right? They finish the job. Okay. So here is an example. Here's an example. This is a fairly gnarly polynomial. We can factor it over R as this. So in this case, 2, the 0, 2 has multiplicity 3. So this is z minus 2 times z minus 2 times z minus 2 times z squared minus 9. So this is fully factored over the real numbers. But if we allow ourselves to work with complex numbers, we can continue to factor this as z minus 3i, z plus 3i. And notice here that if we add up the multiplicities of these factors, 3 plus 1 is 5, which is the degree of that polynomial. How cool is that? How cool is that? So when you look at that degree, that is how many zeros you have as long as you're allowed to work over the complex numbers. Okay, other important corollaries. So, oh wait, oh, not yet. We're going to prove that corollary in just a minute, but I wanted to take a little sidestep here. Just look at how similar this is to the fundamental theorem of arithmetic. We reviewed the fundamental theorem of arithmetic back in chapter 1, and that said every positive integer can be uniquely factored into a product of prime factors. This is the same as the statement for the fundamental theorem of algebra, but applied to polynomials. That's basically the same thing. We even call linear factors prime factors. Yeah, so it's the same idea. There's a reason for that. So one of the reasons that we reviewed that back in chapter 1 and that we're talking about it now is because there is a really beautiful structural equivalence between integers and polynomials. That's not a coincidence, right? Geez, I know one of my old advisors used to say that in mathematics we don't believe in coincidence, but there's a reason that there is this similarity, and it's because there's a structural equivalence that's higher up that you don't know about yet. It's there. And if you want to learn about it, well, go into math and you will learn it. And then you'll realize that not only is there a bigger structural thing going on, but the fundamental theorem of algebra and the fundamental theorem of arithmetic, are just special cases of that larger theory that exists, which is pretty wild. Maybe to be a little more precise, the set of integers and the set of complex polynomials, they're examples of a more general structure called a unique factorization domain. And even more strongly, because each of these structures or each of these collections has a Euclidean division algorithm associated with it, they're part of an even more special structure called Euclidean domains, which can be generalized. So that whole notion of like the division algorithm, that can be generalized even more than what we just saw here. All right. So yes, math majors, you will study and explore such abstract structures. Non-math majors, good news, you don't have to study those if you don't want, but you will get to enjoy all of the applicable benefits of those structures that math majors make sure you've got. Um, my old analysis teacher used to say that mathematicians spend their lives proving that things exist so that the engineers can sleep well at night knowing they exist. There you go. So hope you enjoy that. All right, so we're gonna prove that corollary, the one that says you can factor those polynomials into a product of linear factors. We're gonna prove that. It's definitely worth the proof. We've been appealing to it, we've been using it. We're gonna walk through and go through the proof. Here we go. So let P of z be a complex polynomial. By the fundamental theorem of algebra, it's got to have at least one complex zero. We're gonna call it R1, guaranteed to exist by the fundamental theorem of algebra. Then, by the factor theorem, z minus R1 has to be a factor of that polynomial. By the polynomial division algorithm, we can rewrite, or there exists a quotient, a polynomial Q1, where the degree of Q1 is one less, and Q1 of z has a leading coefficient C sub n, such that we can write P of z as that linear factor times that quotient. There it is. So this is what we kind of saw earlier in this section, right? We basically factored, we found a zero, we factored it out, and then we can write it as this factor times a depressed polynomial, right? Well, guess what? Repeat the process. Repeat the process by the fundamental theorem of algebra again. This polynomial has at least one complex zero. Call it R2. Then, by the factor theorem, z minus R2 is a factor of Q1z. By the polynomial division algorithm, there's another complex polynomial, Qt of z, with degree n minus 2, that still has the leading coefficient C sub n, such that we can now write P of z as this times that. Maybe you can see where this is going. Repeat it again. You can repeat this argument n times. You can use induction, and that will yield that you can factor P of z until you get all of this, where the m sub i's, these things are the multiplicities of those roots, of those zeros. The degree of this final polynomial is zero. So in other words, the degree of this is zero, so that means it's a constant. So that means that that last polynomial is just going to be the coefficient C sub n, the leading coefficient. And then voila, we've done it. Pretty wild, huh? Pretty wild. And yes, so P has exactly n complex roots. I want to flash back to this proof for a minute. Look at how all these pieces are coming together to give us this amazing result. This is just a fundamental truth about polynomials. The fundamental theorem of algebra guarantees the existence of a zero. The factor theorem gives us the connection between zeros and factors. The division algorithm gives us an algorithm for actually factoring that thing, factoring the polynomial we started with by this factor. And we know the degree is going to be exactly one less. So we can get this factorization. Then we can just keep repeating the process until the degree of that resulting quotient is zero. That's it. Cool stuff. Just cool stuff. Got to ponder it for a second. So let's just take a moment of silence to just appreciate how amazing that result is. Wow. What a build up to. What a build up. So much stuff. Okay, now what can we do? What can we do? Well, we have some more important corollaries that are going to help us out. So let's continue with that. This one's called the conjugate pairs theorem. So this is a nice result. If you've got a polynomial function whose coefficients are all real numbers, and you know that you have one complex zero that has an imaginary part, then the conjugate of that zero must also be a zero of the function. So in other words, if you've got a number a plus bi that you know is a zero of the function, then a minus bi must also be a zero of the function. The only caveat to that is the coefficients have to be real numbers. If the coefficients involve imaginary numbers, then there's no guarantee that a conjugate is going to be a zero. So let's look at a simple example, right? Here, look at this polynomial that I gave in factored form to start. Z minus 2i times z plus 2i. Multiply that out, you get z squared plus 4, okay? So z squared plus 4, the coefficients are all real numbers. And by the fundamental theorem of algebra, it has at least one complex zero, at least one complex root, right? Well, here is one of them. Z plus 2i, or sorry, z minus 2i is a factor. But because this is a factor, this also has to be a factor because the coefficients are real. Or, more specifically, because 2i is a zero, negative 2i must also be a zero. Now, compare that to this polynomial down here, g of z. Here, I've got it written in factored form. If I multiply it out, I get this. Now, in this situation, that coefficient is imaginary. So if there are imaginary coefficients, then this corollary may fail. All right, it may fail. The reason for that is the sum of squares formula. So it's the sum of squares formula that is causing those imaginary parts to disappear. And that's why if your coefficients are real numbers and you've got a complex zero with an imaginary part, its conjugate also has to be a zero. That's the idea. Okay, now a consequence of corollary 3 is this additional corollary. There's just so many. They just fall dominoes after you get the fundamental theorem of algebra. Every polynomial function of odd degree with real coefficients has at least one real zero. So, as a maybe kind of a messy looking example, here's a polynomial. It's got an odd degree. All the coefficients are real numbers. There must be at least one real zero. That's it. They can't all be imaginary zeros. They may be irrational, they may be rational, but no matter what, we know there is at least one real zero here. Gotta be, because the degree is odd. Let me give you some visual intuition for that. We haven't talked much about the geometry here, right? We're going to see more of that in the next sections, but think about it like this. What do you remember about odd degree polynomials? Think about that while I draw this quick sketch, right? So if my polynomial is like degree 3, it looks like this. So there's a 0. Maybe it looks like this. So there's a 0. And what this theorem is saying is that no matter what this degree is, as long as it's odd, you're going to have something like that. It's got to happen, got to happen. So if the degree is 3, I'm sorry, if the degree is odd, you're going to have at least one real 0 as long as you've got real coefficients. That's it. Okay. Whew. That's a lot of buildup. That's a lot of theory. Let's use it. Let's use this theory. And this is one that I want you to try on your own, this example, okay? Here's the setup. Find a polynomial p of degree 4 that's got real coefficients. And we know that the zeros are 1, 2, and 3 minus I, okay? I want you to construct a polynomial that has those as zeros with all real coefficients, and I want you to try to write it in standard form, okay? So think about how you'll do it. Now, give your brain that feedback. Verbalize something. What do you know already that given those zeros? What do you know already given those zeros? Okay. And now try to work it out. Try to write out the polynomial. I'll give you a hint. Try to write it in factored form first. Okay. Now let's do it together. Just by the factor theorem, like we've seen even since section 3.2, right? um, this is a zero, this is a zero, and this is a zero. So automatically I know three factors of the polynomial immediately. Without hesitation, I know that I have three factors. There's another thing I know. Because the coefficients are real and this has an imaginary part, the conjugate of this must also be a zero by the conjugate pairs theorem. And that's all I need. So now I know that one of the zeros is one of them is two, one of them is 3 minus I, and the other one is 3 plus I. Let's write it in factored form. Boom. We have that immediately. We have that immediately. And we've seen this a few times now, right? That's the beauty of the factored form. Now to write it in standard form, multiply everything out. I recommend leveraging the sum of squares formula. That can help you out. Here we go. First, what I did was I simplified these. This is going to result in a sum of squares, z minus 3 squared plus I squared, right? There you go. So you get that. I squared is just -1. I also multiplied this out and then combined all the like terms to get this. Now I went through, and I did this part by hand. I just went ahead and did this times that, and then I did that, that, and then I did that, and just wrote out all the results. Then I combined like terms to get this, just like so. Okay, one thing I want to mention here, notice that we were only given the zeros of this function, the zeros of this polynomial. We were not given another point. So we can't actually determine what the leading coefficient is going to be. The leading coefficient could be anything. In fact, whatever this polynomial is, whatever this polynomial is, we only know it up to vertical scaling. So imagine a polynomial that has all of these zeros. Imagine a picture of it, right? Well, we could also take that picture and stretch it, and that would be acceptable, or we could compress it, and that would be acceptable. Any one of those would still be acceptable, unless we had another additional data point. And if we had another additional data point, then we could find the leading coefficient, and it would snap into a single polynomial. That's the idea. Okay, man, I don't know about you, but this is a lot. This is a lot. It's heavy. It's complicated. The polynomials are so long. They're complex. They're real. There's zeros and roots and the division algorithm and all this stuff. Well, this is why we have technology, my friends. This is why we have technology. So, as you can see, once the degree of the polynomial gets even remotely large, even degree 5 kind of makes me wince a little bit, then working with these expressions becomes really tedious and difficult. But luckily, we have technology. We have the technology, okay? Mathematica is one form of this technology. There's a ton. This is why you want to at least be somewhat familiar with mathematical technology. This technology can do everything we've just done way faster than you will ever be able to do it. And guess what? You want to know how it does it? Using the methods that we just learned about in this class. That's how it does it. So a lot of times I like to tell my students, this is the kind of stuff that you will not have to do, but you will definitely know how to tell a computer how to do it because the computer can do it better than you can. That's pretty much it. So what is the human component of this? The human component is the problem solving aspect. It's setting up the problem, constructing the problem, knowing what approach to use to solve the problem. And then you leverage the technology that we have to help you solve that problem. There's an interaction between humans and machines here. Okay, you need to embrace that interaction. Mathematica is going to help us a lot. There are a ton of commands that are perfectly suited for our purposes. The command expand will expand any expression. So, for example, multiplying out a polynomial given in factored form. So, if you didn't want to do this, Mathematica will do it instantly, way faster than you can. You just use the expand command. You enter this in the expand command, and it will expand it to this. That's it. That's it. The other thing is Mathematica can already factor polynomials, and it can even factor them over different algebraic extensions. That's algebraic extensions are basically like number sets with a few other numbers tossed in just to look at the structure. So the command factor is what lets you factor a polynomial over the integers z. So if you plug a polynomial into this command in Mathematica, run it, hit shift return, it'll factor it over the integers pretty instantly as long as the degree is not gigantic. One thing, Mathematica cannot factor expressions over R in general. Why do you think that is? Something for you to ponder real quick. Let me throw up the thinker. Hmm. Can't factor things over R in general. Why is that? But we can specify what irrational or imaginary numbers are allowed in a factorization, and then it can factor using those irrational numbers or imaginary numbers. That's where the command extension comes in. You're basically saying, hey, Mathematica, factor this over the integers, but I'll also let you use square root of 2 and square root of 3. And once you do that, it'll factor. It'll be like, okay, got it. Now I know what I can factor with. Um, that might seem a little bit limited, but again, the technology is more amazing than you might think. Mathematica can find the zeros of a polynomial using the command roots. Roots, and you basically set up the polynomial equation and it will compute the roots. Only downside with that, maybe not too much of a downside, is that it can only approximate irrational roots. Keep that in mind. This is why we talked about the theory of approximation. If there is a rational root, Mathematica will give it to you exactly. If there is an irrational root, it can only approximate it. Again, because irrational numbers, they've got infinite decimal representations. Mathematica is just going to get close as you want it to get, but it'll get close, okay? You can also create really amazing plots and visualizations. We're not going to go too much into detail with those, but you will have to do it in a basic way in the activity for this section. Let me do this. Let me pull up Mathematica now, and let's explore this really, really cool technology. Okay, here we go. So I want to go back to example 9. That one is this polynomial here, 2 times x to the fifth plus 13x squared minus 3x minus 6. And what I did was I instantiated it as a function. I called it f, f bracket x subscript. The subscript lets it know that x is the variable. And I'm going to define it as this polynomial. And if you remember, we used the rational roots theorem and we came up with all the possible rational roots. It was like plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 3 halves, I think, something like that, right? And we didn't check them. We just said, okay, if there's rational roots, it's got to be one of those in the list. I think there were like 12 of them, right? Well, here I'm going to use this command, roots f of x equals 0. If you want to give Mathematica an equation, you use a double equal sign just to differentiate between a standard equal sign. So here I'm saying this is an equation, f of x equals 0. That's the polynomial equation. And I want Mathematica to find the roots of this equation, and I'm telling it that the variable is x. Okay, so the variable that it is solving for is x. Now I'm going to compile it. Boom. And that's how quick it is. So check out these results. X equals this number, X equals this number, X equals this number, this number. Uh, you notice how these all have little dot dot dots, right? Oh, these vertical lines, that just means or. X equals this, or X equals this, or X equals that, or X equals that, or X equals that. So check this out. For one, the dot 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 is occurring because whatever this root is, it's irrational. It's not a rational number. So it's computing the fifth root of something, right? Um, this is just telling you how it computed it. If you wanted it to more degrees of accuracy, like more decimal places, you can tell it to do that just by specifying it. Here, this is an irrational root. This is an irrational root. This root, not only is it irrational, but it's also imaginary. It's got an imaginary part. That's what that I is that you see right there. And here, the real and imaginary parts are irrational numbers. So, yeesh. And then here is the conjugate, right? Notice this is the conjugate. It's 0.834 blah 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 minus 1.7 blah 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 I, 0.834 blah 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 plus 1.7 blah 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 I, because these two are conjugates. That's the conjugate pairs theorem in action, because look, all of these coefficients are real numbers. All these coefficients are real numbers. So that means if even one of these zeros has an imaginary part, then its conjugate must also be a zero. But again, this is a situation where this polynomial, which looks pretty simple, has no rational roots. So that whole exploration of looking for the rational roots didn't really help in this case. But thankfully, Mathematica can look for it numerically using a numerical approximation method, which you'll learn about in your later courses. You'll learn one in Calc 1, you'll talk more about them as you move along. That's why we like this technology. Okay, now let's look at example 10. Um, this one, oh wait, did we even get to example 10 yet? Example 10, I think we did. Oh yes, that's right. Oh yeah, that's right. We did this one. So remember, this is the long one where I started out by saying, hey, just find the rational roots. And then we went through the whole process, right, of factoring it. So here it is. I'm instantiating it as a function, g of x, right? And now I'm going to use the factor command. I'm just telling Mathematica to factor this. Let's see what it gives. Boom. It writes constants before variables, so it kind of changes the order here. -2 plus x, that's x minus 2. This is x minus 1. This is x squared plus 9. It just writes it in, I'll say reverse standard order. But notice here, this is a linear factor, this is a linear factor, but this is a quadratic factor. So the factor command only factors over the integers, right? If we want it to factor this sum of squares, we need to allow it to do so using the extension command option. So this basically says, hey, Mathematica, factor g of x, but you're allowed to use imaginary numbers. That's what it's saying. Here, the capital I, that is the imaginary unit. Um, uh, Basically, this will render as this little fancy I that you see right here, okay? So Mathematica uses a capital I to represent the imaginary unit. Let's try it now. Boom. So same result as above, but now it is able to factor this as this product, x minus 3i, x plus 3i, conjugates, right? There we go. Let's use the roots function. Let's use the root function again. So here, looking at the factorization, we can pick out the zeros, right? So it's going to be 2, 1, 3i, and -3i. Those are all the zeros, the roots of the polynomial equation. Or we can have Mathematica do it directly, and it just lists them all out. X equals 3i, or x equals -3i, or x equals 1, or x equals 2, and it doubles it because the multiplicity of this root is 2. There it is. So it lists them all out. Pretty cool technology, huh? Okay, next, let me flip back to the slides for a second, just to just to really scare you for a sec, I guess. What if we had to find the real and imaginary zeros of this polynomial right here? What about that one? That one you should be like, what are you talking about, right? I would. Well, good news. This would be a nightmare to do by hand. No human would ever be asked to do this by hand these days. This is not the job of a human being to factor this and to find the zeros of this. This is a problem that is ripe for a computer to do. It is ripe for Mathematica to do. Um, yeah, so I'll say this. You wouldn't have to do it by hand, but many of you will be asked to solve this problem using a computer. So it's good to know how to do it. It's a root finding problem. It is a standard root finding problem. Find the roots of a polynomial, one of the most basic root finding problems you'll ever see. But this is why we have technology, all right? So this kind of jumps the gun a little bit, but let's look at Mathematica and see what Mathematica will give us. All right, here again, I instantiated the polynomial, P of z, it's a mess. It's a mess, but pretty normal for what you would see a computer trying to do. Let's factor it. Boom, Mathematica factored it. There's some linear factors, right? Linear, linear, linear. There's some repeated factors, linear, linear. Quadratic factors. See, these are not factorable over the integer or the real numbers. Uh, these are not factorable over the integers either. So I need to tell Mathematica to allow imaginary numbers. So I'm going to extend the integers with the imaginary unit I. Try it again, Mathematica. Boom, there it is. Fully factored. Every factor is linear. Fundamental theorem of algebra, or that corollary, I should say. Looks like we got one repeated factor. And yeah, now if we could read off all of the roots. We could read off all the zeros, right? Let's just have Mathematica find them for us. There we go. Now I can easily read them off. Z equals 1/5 I, Z equals -1/5 I, Z equals 4I, -4I, 4/7. Look, rational root. These are, in fact, these are all rational or imaginary. Couple of repeats. There you go. I love technology. There you go. That's why we have it, okay? Um, Same thing we just did, and these are all the roots. You can just read them right off from Mathematica. Cool stuff. Okay, all right, enough of my rambling. Let's play. This is one of the computer lab activities we're going to do. We are going to practice using Mathematica just so that you can see how nice it is. It's always good to get some basic exposure to these things. Yeah, just a word from even my advisors, a word from the wise. Get comfortable with mathematical technology, get comfortable with computers. Don't go all the way through your undergraduate program or whatever program you're in without getting some familiarity with computers and programming, all right? Okay, I'll end it here. Thank you all for bearing with me, and I will see you next time when we talk about rational functions and their local behavior. Take care, everyone.